In this module, we zoom into the conversation between CometBFT and your Cosmos SDK app. ABCI++ is the protocol boundary where consensus decisions meet application logic. Understanding this lifecycle is crucial if you want to safely inject custom behavior into block proposal and commit. Every block in a Cosmos SDK chain moves through a predictable lifecycle. First, a proposer assembles a block from mempool transactions. This is the earliest point where ABCI++ can influence which transactions even get a chance. Next, other validators validate the proposal. They run basic checks, verify signatures, and enforce any extra rules your application defines. Then comes voting, where validators run consensus to either accept or reject that proposal. If it's accepted, the application executes each transaction in order, updating in memory state. Finally, the app commits. It persists state, produces a new state root, and consensus advances to the next height. Phase 1 is where a block is actually born. CometBFT has already run leader election and chosen a proposer for a specific height and round. That proposer calls PrepareProposal on the application and asks, given this mempool, what block should I build? Your app receives a batch of candidate transactions plus some metadata. Here you can aggressively shape the block, drop spam, cap gas, prioritize certain message types, or inject system transactions. After filtering and reordering, you return a finalized list of operations, and CometBFT wraps that into the proposal it gossips to other validators. Once the proposer has built a block, every other validator has to judge it. This is where ProcessProposal comes in. CometBFT hands the proposed block to your application. Your code runs whatever policy you define: invariant checks, anti-spam rules, per block limits, even application-level slashing conditions. The key constraint is determinism. Given the same proposal and state, every honest node must return the same answer: accept or reject. That answer directly controls the validator's prevote. If enough validators reject, the block can't be committed, and your chain's global safety rules are enforced. Once consensus decides on a block, the application's state machine takes over. BeginBlock ingests the block header, evidence of misbehavior, and any consensus metadata. This is where you update things like slashing, proposer rewards, or time-based logic. Then, DeliverTx runs each transaction in the exact order agreed by consensus. Determinism is critical here. Same order, same code, same resulting state on every node. EndBlock lets you finalize block-level changes, especially validator set updates. Finally, commit persists the new state to storage and returns the AppHash, which becomes the cryptographic anchor for the next block. Vote extensions let your application sneak extra information into the consensus path without changing the core protocol. With ExtendVote, each validator can attach an app-defined payload to its pre-commit, a state root, a proof, or any compact commitment. Then VerifyVote extension runs on the receiving side and decides whether that extra data is well-formed, consistent with local state, and worth accepting. With that loop in place, you can implement in-protocol oracles, data availability or fraud-proof commitments, or liveness checks that other validators can independently verify and act on. ABCI++ gives you powerful hooks, but they don't run in a vacuum. Every callback operates inside hard consensus limits: maximum block bytes, maximum gas, evidence windows, and more. These are global rules that every validator must enforce identically. If your application logic tries to exceed them, the proposal is simply rejected by CometBFT. You control these limits through consensus params, so tuning them is effectively tuning the safety and throughput envelope of your chain. When you implement PrepareProposal, treat it as a constrained packing problem. You have a stream of candidate transactions, but you're bounded by max bytes and max gas. So you iterate through the mempool in some deterministic order, often by fee or a custom priority score, and track cumulative size and gas as you go. As soon as adding the next transaction would cross a limit, you stop or skip it. The goal isn't to cram everything in. It's to maximize economic value and application importance while staying comfortably below the rejection thresholds that would cause the whole proposal to be discarded. ProcessProposal runs on every validator, and it must make the exact same decision everywhere. That means no randomness, no local clocks, no environment-dependent checks, and no calls to external services. All logic has to depend only on universally available state, the proposal itself, the current chain state, and consensus parameters. If two honest nodes with the same state can ever disagree on accept versus reject, you've just broken safety. In ABCI++, the fastest way to a catastrophic fork is sneaking non-determinism into ProcessProposal. Treat determinism here as an absolute, non-negotiable rule. When you handle errors in ABCI++ callbacks, always ask, does this indicate bad input or a broken chain state? If it's just a bad transaction or proposal, treat it as recoverable. Reject the transaction or mark the proposal invalid, but let the node keep running. You want the chain to continue making progress while filtering out garbage or malicious input. If the error suggests an invariant is broken or state is corrupted, that's unrecoverable. In that case, you should panic or return a fatal error code, deliberately halting the application so operators can investigate before more blocks are produced. When you design ABCI++ logic, assume some proposers are adversarial. A rogue proposer can ignore block size limits, reorder transactions to front run, or selectively drop transactions to censor users. At the same time, some validators might be lazy or misconfigured and just accept whatever proposal they see. ProcessProposal is where you stop all of that. Think of it as an application-level firewall. Every proposed block must pass your checks before you even consider voting. Here you reinforce limits, verify structure and state transitions, and decide whether honest validators accept or collectively reject this block. Heavy computation inside ABCI++ callbacks doesn't just make blocks slower, it directly attacks liveness. CometBFT has fixed timeouts for proposal, pre-vote, and pre-commit. If your PrepareProposal or ProcessProposal work spikes above that budget, validators start missing deadlines, rounds repeat, and the network looks unstable even though the code is technically correct. The practical rule: callbacks should be mostly lightweight policy and filtering. Push expensive business logic, large proofs, and deep validation into DeliverTx where it doesn't gate consensus progress. When in doubt, profile your callbacks under worst-case load and design assuming the slowest validator in the set. As you start wiring ABCI++ into your app, treat these as non-negotiable guardrails. First, every decision must be deterministic and derived only from shared, verifiable state. No randomness, no clocks, no external APIs. Second, enforce hard limits yourself. Cap gas, bytes, and any per-block work. Third, ruthlessly optimize hot paths in PrepareProposal and ProcessProposal. Target O, n log n at worst, and avoid disk I/O. Fourth, surface-rich, structured logs and consistent error codes. Finally, test adversarially. Fuzz malformed proposals and vote extensions until nothing surprising happens. ABCI++ gives you a programmable pipeline around consensus, not just a place to run transactions. You shape the block at proposal creation, deciding which transactions are even eligible. You defend your rules during proposal validation, rejecting blocks that violate application invariants. During voting, vote extensions let validators attach extra evidence or commitments that your app can verify. Then execution applies transactions, and state commitment seals those changes into the canonical state root. The real skill is designing state machines that use each callback deliberately, so you gain flexibility and performance without risking safety or liveness.